The Milky Way galaxy spans roughly 100,000 light-years from edge to edge. At that scale, the word near loses its everyday utility. To study the stars closest to us, we have to isolate a microscopic fraction of the total galactic volume. To build this map, we use our own star, the Sun, as the absolute center point. Every coordinate, distance measurement, and orbital trajectory is calculated relative to this single anchor. Navigating this volume requires more than vague descriptions of proximity. Astronomers define the neighborhood by slicing the space around the Sun into nested geometric spheres, each serving a different scientific purpose. The first boundary is the innermost neighborhood, stretching out to a radius of 20 light-years. This 20 light-year volume contains roughly 130 known objects. It is small enough to discuss systems by name and includes our most famous named neighbors, like Alpha Centauri and Sirius. Expanding further, we reach the 10 parsec sample, which equates to 32.6 light-years. This sphere is the scientific benchmark for the neighborhood. The volume is large enough to provide a statistically significant population of stars, yet small enough to maintain a highly complete census of even the faintest objects. Finally, the Gaia catalog of nearby stars extends out to 100 parsecs, or about 326 light-years. This volume contains over 331,000 objects. These nested spheres provide the coordinates required to organize the local population. They turn the surrounding vacuum into a searchable inventory for statistical study. Placing a star accurately within this 3D model is difficult because the night sky appears as a flat, two-dimensional projection. From Earth, a star's position is clear, but its actual depth is hidden. To find that depth, astronomers use trigonometric parallax. As Earth orbits the Sun, our perspective on nearby stars changes. Because of this movement, a foreground star appears to perform a measurable visual shift against the static, distant background of galaxies. Measuring the angle of that shift allows us to triangulate the star's distance. However, these angles are so small that they require micro-arc-second precision, a level of detail that requires observing from above the Earth's atmosphere. The modern engine for these measurements is the European Space Agency's Gaia Space Observatory. Gaia has tracked the positions of nearly 2 billion stars, and its primary impact on the local map is its ability to detect the intrinsically faint, nearly invisible sources that previous optical surveys missed. To complete the 10 parsec census, we have to find objects that emit very little light: cool red dwarfs, substellar brown dwarfs, and faint companions orbiting brighter stars. Mapping the solar neighborhood is effectively a forensic task, identifying an environment that is mostly too dim for the human eye to perceive. When those faint objects are plotted into the 3D model, the 10 parsec sphere reveals a staggering sparseness. The mean spacing between stellar systems in our neighborhood is roughly 7.2 light-years. In a volume that contains hundreds of objects, the statistical reality is a landscape defined by immense empty gaps. If we rotate our view into 3 dimensions, stars that look clustered together from Earth are revealed to be separated by trillions of kilometers of vacuum. Even in our most crowded maps, the defining characteristic of the solar neighborhood is physical isolation. The stars that manage to bridge these gaps determine the environment of any local planets, and the demographics of our neighbors are not what we might expect. More than 60% of the stars in the 10 parsec sample are M-type red dwarfs, objects significantly smaller and cooler than the Sun. Solitary, Sun-like G-type stars are a minority. In our immediate vicinity, the Sun is an outlier. Our neighborhood map shows a local universe that is predominantly dim and red, with environments very different from our own solar system. Within this red population, the Alpha Centauri triple system is our absolute nearest neighbor, located 4.2 light-years away. Slightly further is Barnard star, the closest single star, which hosts a compact architecture of 4 sub-Earth planets. We also track substellar objects like Luhman 16, a binary pair of brown dwarfs that never reach the mass required to sustain hydrogen fusion. This population is also in constant motion. Every star in the map has its own trajectory, meaning our neighbor list changes as stars drift in and out of the solar vicinity over millions of years. In 1.3 million years, the star Gliese 710 is projected to pass within 0.06 parsecs of the Sun, a distance that penetrates the outer Oort cloud. The solar neighborhood is a sparse, dim environment that is constantly in motion. These coordinates represent the limit of our highest precision data, a local laboratory for studying how stars and planets actually behave. When you look up at the night sky, you see thousands of brilliant, massive stars piercing the darkness. That view creates a compelling illusion that the Milky Way is a crowded, glowing city of giant suns. But to understand what our galactic neighborhood actually looks like, we have to look past the stars we can see with the naked eye. If we launch out from the solar system on a strict 10.5 light-year flight, the population of space looks drastically different. We leave the brilliant giants behind and enter a realm dominated by the dim and the small. Our first stop is roughly 4.3 light-years away at the Alpha Centauri system. Here, we do find something familiar. Alpha Centauri A is a yellow star, almost identical to our Sun, tightly locked in a gravitational dance with a slightly smaller, cooler companion, Alpha Centauri B. But neither of those is actually our closest neighbor. That title belongs to a third star bound to this system, Proxima Centauri. It sits slightly closer to this, at about 4.25 light-years. Proxima is a red dwarf, a small, faint, highly active star that puts out a tiny fraction of the Sun's light. This map shows the confirmed planetary architecture orbiting that tiny star. Proxima Centauri hosts at least 2 known worlds. Proxima b is a rocky planet receiving temperate levels of radiation, while Proxima d is a sub-Earth mass world locked in a blistering 5-day orbit. You'll notice a third dotted path further out. That represents a longer period signal attributed to a candidate planet called Proxima c. Recent astronomical data has thrown this signal into question, leaving it heavily debated and unconfirmed. This means right next door, at our absolute closest stellar encounter, we find a highly irradiated, volatile red dwarf instead of a peaceful sun-like environment. Proximity does not guarantee an Earth twin. Pushing outward to 5.96 light-years, we encounter Barnard's star, the closest solitary star to Earth. It's another small red dwarf, but it is moving rapidly laterally across our sky, boasting the highest proper motion of any known star. This diagram compares the architecture of Barnard's star against our own inner solar system. Thanks to next-generation instruments measuring tiny radial velocity wobbles in the star's motion, astronomers recently confirmed 4 sub-Earth mass planets here. And as you can see, all 4 orbits are packed tightly inside the equivalent distance of Mercury. Because these planets formed so efficiently and migrated inward, data confidently rules out any traditional habitable zone Earth twins further out. As we continue our flight, we hit a physical limit with standard optical telescopes. To map the rest of this volume, we must switch to infrared sensors to detect objects lacking the mass to ignite hydrogen fusion. At 6.5 light-years, those infrared sensors reveal Luhman 16. This is a binary system made entirely of brown dwarfs, failed stars that straddle the physical boundary where atmospheres transition from gaseous stellar layers into heavy chemical cloud decks. Push just a bit further to 7.4 light-years, and we find WISE 0855-0714. This object is a sub-brown dwarf. It emits almost no visible light, and its surface temperature sits below the freezing point of water, making it closely resemble a frigid planetary atmosphere drifting alone in space. For centuries, traditional optical stargazing missed a massive portion of our local neighborhood. We needed modern infrared surveys to finally expose these freezing, dark masses hiding right in our own backyard. Let's expand our spatial flight out to a hard boundary of 10.5 light-years. As we survey the remaining objects in this volume, a pattern of intense stellar volatility emerges. Stars like Wolf 359, Ross 154, and the Luton 7268 binary all belong to a category known as flare stars. These are fully convective red dwarfs, prone to sudden, violent magnetic eruptions that blast their surrounding space with intense radiation. Compare that dim, chaotic environment to Sirius, located 8.6 light-years away. Sirius is a massive, scorching hot star and the brightest object in Earth's night sky. But within this local volume, it is a complete statistical anomaly. The rest of the neighborhood follows the red dwarf rule. There is Lalande 21815, a high-value target for exoplanet searches, and there is Ross 248, a fast-moving dwarf that will actually overtake Proxima Centauri to become our absolute closest stellar neighbor in about 36,000 years. We finally hit our 10.5 light-year boundary at Epsilon Eridani. This is a young, active K-type dwarf, surrounded by a massive, vibrant debris disk and at least one reported giant planet. This chart translates everything we just visited into a strict statistical census. We are looking at a cross-section of the 10.5 light-year sphere, plotting the systems strictly by distance, and exaggerating their sizes to show the physical distribution of star types. The data is clear. Massive, bright stars are the rare exceptions. The overwhelming majority of our immediate galactic environment is made up of dim red dwarfs and invisible substellar objects. Naked eye brightness is a terrible judge of physical reality. Our sun does not exist in a crowded realm of brilliant stars. It travels through a dark, densely packed neighborhood composed mostly of faint, extreme dwarfs. For thousands of years, humanity mapped a beautifully illuminated illusion. Looking at antique celestial maps like this one, early astronomers charted a sky filled with brilliant, solitary stars, arranged into grand constellations. Because our eyes can only detect the most luminous objects, we developed a massive statistical bias. We assumed the brilliant beacons we could see at night represented the typical inhabitants of our galactic neighborhood. This chart breaks down the Gaia-era census of stars within roughly 32 light-years of Earth. The columns for Sun-like G and K-type stars are completely overshadowed by M-type red dwarfs, which make up 61% of the local population. Zooming in closer to our innermost 20 light-years, the density is even more extreme. Out of the 103 known main sequence stars here, 80 are red dwarfs. Our Sun is a demographic anomaly. The true standard for a star in our local universe is a faint, dim red dwarf. These low-mass stars operate entirely differently than the Sun. They are fully convective, meaning their interiors churn continuously from core to surface, resulting in highly turbulent, deeply red bodies that fuse hydrogen at an incredibly slow rate. Because they burn through their fuel so slowly and efficiently, their biological lifespans stretch far beyond the current age of the universe, projected to last for tens of trillions of years. This extreme longevity creates a unique mathematical certainty. Every single red dwarf that has ever formed since the dawn of the galaxy is still on the main sequence, burning today. Yet their extreme faintness kept this massive population completely hidden from early astronomers. It took the advent of high-precision astrometry and modern infrared surveys to finally detect their faint glow and chart their positions. The space immediately around us functions as a permanent, slowly burning archive, preserving the oldest and most common stellar engines the galaxy has to offer. If we drop below the mass of a red dwarf, we hit a hard physical limit. We enter a regime of objects that lack the gravitational weight required to sustain steady hydrogen fusion in their cores. These substellar objects are known as brown dwarfs. Because they cannot fuse hydrogen to generate new energy, they spend their entire existence simply cooling and fading into the dark. As they cool, they radiate their residual heat almost entirely in the infrared spectrum. To a standard optical telescope, they are functionally invisible. Even the Gaia Space Observatory, an astrometric powerhouse that has mapped over 1 billion stars with pinpoint precision, reaches its limits here. Its optical sensors entirely miss the coldest of these free-floating bodies. At the extreme edge of this population are Y dwarfs, like WISE 0855-0714, located just over 7 light-years away. Its surface temperature hovers around the freezing point of water, making it as cold as Earth's polar regions. A significant fraction of the mass in our immediate neighborhood belongs to this hidden, dark population, completely undetectable without highly specialized heat-sensing instruments. At the opposite end of the stellar life cycle lies another hidden population, the degenerate remnants known as white dwarfs. These are the ultra-dense, dead cores left behind after intermediate mass stars exhaust their fuel and violently expel their outer gaseous layers. One prominent local example is Van Maanen star, a solitary white dwarf 14 light-years away that acts as a forensic window into long-dead planetary systems. A white dwarf's immense surface gravity should pull heavy elements down into its core almost instantly, leaving a clean atmosphere. Yet Van Maanen's star is heavily polluted with calcium and iron. This means it is actively shredding and accreting the rocky debris of planets that survived its chaotic red giant phase. Our solar neighborhood is an active graveyard, a place where the shattered physical remains of ancient terrestrial worlds are currently being consumed by the stars they once orbited. When we map these red dwarfs, cooling brown dwarfs, and dense white dwarfs together, we can break the final historical illusion of the night sky, the idea that stars exist in isolated solitude. The true governing architecture of the local census is multiplicity. Looking at this abstract orbital diagram of the 10-parsec census, we see that a staggering percentage of our stellar neighbors do not orbit alone. They are locked in gravitationally bound systems of doubles, triples, and even quadruples. This intense, hierarchical gravitational interplay dictates exactly where protoplanetary disks can condense, and how any resulting planets might remain stable over billions of years. For astronomers, these overlapping orbits and constant gravitational tugs create massive observational complications, masking the delicate, low-mass signals of terrestrial exoplanets hidden within them. The true map of the solar neighborhood is a deeply layered, chaotic kinetic mobile of faint and dead stars. Understanding that architecture provides the only valid rulebook for hunting the planets concealed within it. The spherical volume extending 15 light-years from our Sun contains roughly 52 primary stellar systems. This is our immediate galactic neighborhood. The scientific value of this local census is dictated entirely by observational geometry, rather than any inherent astrobiological probability. We target these specific stars because their physical location makes measurement possible. This principle is known as the proximity premium. When a stellar system is located within a few parsecs of Earth, the flood of incoming photons allows astronomers to resolve mathematically faint planetary signals that would otherwise remain invisible. A rocky planet orbiting a dwarf star at 3 parsecs generates a distinct, measurable signature. If that exact same system were placed at 300 parsecs, the inverse square law degrades the data quality so severely that the planet vanishes from our instruments entirely. To capitalize on this geometric advantage, institutions have dedicated massive ground-based infrastructure to monitoring these specific nearby skies, filtering out the ambient noise of the galaxy to isolate local data. Extreme proximity guarantees our ability to detect these worlds with absolute precision. It absolutely does not guarantee that the worlds we find are hospitable to life. This diagram illustrates the radial velocity method, where a star and its planet orbit a shared center of mass, known as a barycenter. As the star is pulled toward and away from Earth, its light shifts in frequency. A closer star delivers a massive increase in captured light. This dense photon count exponentially magnifies the apparent amplitude of the radial velocity wobble in our data, allowing us to detect the microscopic gravitational pull of low-mass planets. For direct imaging, distance dictates angular separation. When a system is brought to within a few light-years, the physical gap between the star and the planet visually widens on our sensors, allowing us to physically separate the planet's faint light from the star's blinding glare. For atmospheric spectroscopy, proximity is the only way to gather enough light to read chemical signatures. As the star's light passes through the planet's atmosphere, high photon counts produce a crisp, readable absorption spectrum. Deep space target systems simply cannot provide the sustained photon density required to construct these detailed atmospheric profiles. The signal-to-noise ratio is too low. These 3 physical advantages explain why the local stellar neighborhood consumes a disproportionate amount of global telescope time. We have the perfect geometry to detect these planetary architectures. We now have to confront the violent reality of the stars they orbit. The closest star to the Sun is Proxima Centauri, a fully convective M-dwarf, or red dwarf, located 4.25 light-years away in the Alpha Centauri system. Its most prominent planet, Proxima b, has a mass equal to Earth and receives temperate stellar irradiation. The system also contains Proxima d, an interior sub-Earth locked in a tight 5.12-day orbit, receiving intense, sterilizing heat. The fact that Proxima b has Earth-like mass and temperate irradiation often leads to it being labeled as Earth-like. That label fails to account for the severe habitability bottlenecks inherent to M-dwarf stars. Because a red dwarf emits very little energy, its habitable zone sits extremely close to the stellar surface. At this proximity, the host star's gravity forces the planet into tidal locking, leaving one hemisphere permanently baked in daylight and the other frozen in perpetual darkness. Furthermore, M-dwarfs are highly volatile. They frequently unleash extreme ultraviolet stellar flares that bombard close-in planets. The direct consequence of this intense radiation is hydrodynamic atmospheric escape. The stellar wind physically boils away the planet's atmospheric gases, stripping it of water and volatiles over billions of years. Proxima b demonstrates that a planet can occupy the exact mathematical parameters of a habitable zone while being actively sterilized by its host star. Moving outward to a distance of 5.96 light-years, we find Barnard star, the nearest single star to the solar system. Recent rigorous observation campaigns have confirmed an incredibly compact planetary architecture here, identifying 4 distinct sub-Earth mass planets tightly packed around the host. The detection of these tiny worlds represents a triumph of precision engineering. The instruments housed in these isolated observatories successfully isolated radio velocity signals below 50 centimeters per second, meaning they tracked the star moving at roughly human walking speed. Despite pushing modern spectroscopy to its absolute limits, the Barnard star system provides an astrobiological dead end. All 4 known planets orbit far too close to the star. Their equilibrium temperatures easily exceed the threshold for liquid surface water. Crucially, this same ultra-precise data sets a firm upper limit on the rest of the system. We confidently rule out planets larger than 0.57 Earth masses in the habitable zone. Barnard star enforces a strict dividing line in astrophysics. Measuring a microscopic planetary signal does not equate to finding a suitable home for biology. This 3D matrix maps the broader 15 light-year volume, filtering the highest priority local targets against their host star's behavioral profile. Ross 128b is a premier target. It is temperate and close to Earth's mass, but its true value lies in its quiescent host star, which exhibits drastically lower flare activity. Teagarden's star harbors multiple Earth mass planets. Similarly, GJ1061 and Wolf 1061 demonstrate that highly compact multi-planet systems are the standard local structural outcome. Tau Ceti is a valuable nearby sun-like star. However, its flashing caution indicator reflects that its planetary inventory remains heavily debated, with some candidates listed as false positives. This matrix filters the noise of the local census, proving that target viability depends entirely on the specific magnetic temperament of individual red dwarfs. The data shows no perfect Earth twin in our immediate vicinity. Instead, it offers a diverse spectrum of heavily irradiated, tidally locked rocky worlds. The 15 light-year neighborhood serves as the ultimate calibration volume for modern astrophysics. The demographics here are an exact reflection of the galactic initial mass function. Low-mass M-dwarfs will always dominate the population by sheer number. These 2 bounding boxes illustrate the strict boundary of our current knowledge. We have successfully confirmed the physics of detection. We know these planets exist, their mass and orbits. What we lack entirely is data confirming they possess stable atmospheres or chemical bias signatures. Placed in their broader galactic context, these few dozen stellar systems are just the absolute closest grain of sand on a vast beach. Because of their proximity, these specific stars will dominate the target lists for the next generation of direct imaging telescopes and atmospheric spectrographs. Extreme proximity dramatically improves our capacity to study the physics of a planet. It does absolutely nothing to change the intrinsic probability of finding biology on its surface. We often visualize the stars near the sun as a permanent geography, fixed points on a three-dimensional map. In reality, the local neighborhood is a scene of constant transit. Over thousands and millions of years, every star follows an independent, high-velocity path that will eventually carry it out of our sight. The stars we call our closest neighbors today are temporary residents. Objects like Proxima Centauri, Barnard star, Ross 248, and Gliese 710 are sweeping across our field of view on trajectories that will eventually redraw our entire local sky. Tracking this movement requires a framework called six-dimensional phase space. Astronomers must plot a star's exact position in three spatial dimensions and then combine those coordinates with three distinct measurements of its velocity. The first component is trigonometric parallax. By measuring how a star appears to shift against the background as Earth orbits the Sun, we can calculate its exact geometric distance and anchor it in space. Next is proper motion. This measurement tracks the star's observable sideways movement across the celestial sphere over time, showing us its transverse speed relative to our line of sight. Finally, we measure radial velocity. By analyzing the Doppler shift in the star's light, we can determine how fast it is moving directly toward or away from the solar system. By combining these 6 data points, astronomers can move past static observations. We can now run a predictive simulation of the galaxy, seeing where every star has been and where they are all going. Our current data shows that Alpha Centauri and Proxima Centauri are still drawing closer to us. In roughly 27,000 years, they will reach their absolute closest approach of about 3 light-years before they finally begin to recede. This timeline tracks the trajectory of Barnard's star, which possesses the highest proper motion of any known star. It is moving so fast that in just 11,800 years, it will reach its own closest approach to the Sun, passing just 3.75 light-years away. But the map keeps shifting. Eventually, the faint red dwarf Ross 248 overtakes the Centauri system. In about 36,000 years, its trajectory will bring it closer to the Sun than any other star, briefly claiming the title of our nearest neighbor. These encounters show how dynamic the neighborhood is, yet they also emphasize its scale. Even at their closest points, these stars remain trillions of miles away, passing through without disrupting the orbits of our planets. If we push the simulation ahead 1.3 million years, we encounter the most significant flyby in our recorded future, the approach of Gliese 710. Gaia predicts Gliese 710 will plunge directly into the Oort cloud, passing within 10,600 astronomical units of the Sun. A star this massive will gravitationally perturb millions of icy bodies, likely triggering a protracted comet shower toward the inner planets. To understand these movements, we have to look at the environment the Sun is moving through. We are currently inside the local bubble, a 1,000 light-year-wide cavity of high-temperature gas created by ancient supernovae. Within this bubble, the Sun navigates a series of warm, partially ionized clouds. These wispy structures fill the space between the stars, shaping the interstellar medium our solar system must traverse. Stars do not move through a void. Their history is shaped by the dynamic environment of the Milky Way, navigating through gas clouds, intense stellar winds, and the remnants of stars that died millions of years ago. Returning to the present day, we can use these dynamic models to summarize what our neighborhood actually looks like within our 50 light-year survey limit. This demographic chart shows the census within that 50 light-year sphere. The local volume is overwhelmingly dominated by faint, low-mass red dwarfs. Stars like our Sun are the rare exception in a neighborhood crowded with smaller, dimmer objects. There is more complexity hidden in these numbers. Many of these systems are binaries or triples, and a significant population of white dwarfs and substellar brown dwarfs fade into the background, invisible to all but our most sensitive surveys. This census identifies the highest value targets for future observations, but proximity to these red dwarfs does not ensure habitability. Many of our nearest planets face extreme radiation and tidal forces that distinguish them sharply from the environment of Earth. Our ability to build this dynamic model rests on the European Space Agency's Gaia mission. Its micro-arcsecond precision has allowed us to map the positions and velocities of over 1 billion stars with unprecedented detail. As new data releases and next-generation observatories come online, we will continue to refine these orbital timelines and discover the hidden companions that still linger in the dark between our neighbors. The stars near Sol represent a snapshot of a moving system. Our local atlas is a continually updating model of objects in transit, reflecting a solar system that is briefly passing through a much larger shifting clockwork.